Ladies and gentlemen, today we gather here to delve into a captivating topic that explores the impact of smiles on face recognition accuracy. Our research team, consisting of me, Shopnil De, Mohammad Musharraf Hussain, Asif Mustafa Hassan, Dr. A.K.M. Ashikur Rahman, and Tamima Tarin, has undertaken an intriguing journey into the understanding of the role of smiles in face recognition accuracy. First, let us reflect on the motivation behind the study. Face recognition technology plays a vital role in various domains such as security, identity verification, access control, and personalized user experiences. However, current face recognition systems face several challenges. Varying light conditions, pose variations, expressions, occlusions, and computational cost hinder their accuracy. In this context, we recognize the significance of facial recognition, particularly smiles, in human communication and emotion recognition. Smiles are universally recognized as a positive and joyful expression, transcending cultural and language barriers. Furthermore, we are fortunate to have an abundance of smiling faces and data available for testing in real-life scenarios. Based on this motivation, we have hypothesized that the facial expressions, including smiles, may significantly impact the accuracy of the face recognition systems. Our research aims to shed light on this unexplored facet and investigate the potential implications of improved accuracy. To enrich our understanding of the impact of smiles on face recognition, we have explored related works conducted by other researchers. One study conducted by Mileva and Burton in 2019 revealed that an open-mouth smile changes the face in an idiosyncratic way, leading to improved unfamiliar face matching performance. Additionally, she explored the effectiveness of landmarks and the geometry for face recognition. They found that well-normalized Euclidean distances and spatial ratios of landmarks can be exploited for accurate recognition. Moreover, O7 in 2017 demonstrated the usability of distance and slope between landmarks in face recognition. Their research showed the statistically significant correlations between landmarks and face recognition tasks. Continuing our exploration, Zhu Hong in 2017 proposed a novel technique based on facial landmark detection, incorporating orthogonal projection and Euclidean transformation to bypass perspective constraints. They used well-normalized distances and ratios for accurate recognition as well. Sarsanov developed a face recognition technique that involved face detection, head position estimation, feature extraction, and testing classifier. They utilized well-normalized distances and ratios based on landmarks as well. Furthermore, we have considered alternatives to facial landmarks, such as deep convolution neural networks, Siamese networks, and 3D face recognition. Characteristics and texture-based techniques like local binary patterns, Gabor filters, and eigenfaces have also been explored. Now, you may wonder why we chose facial landmarks as a focus in our research. Facial landmarks offer a consistent and standardized framework for feature extraction. They allow for precise alignment and normalization, reducing variation due to pose, scale, and rotation. Importantly, landmark-based approaches have been extensively studied and validated in the field of face recognition, providing a solid foundation for further advancements.
Now we'll talk about the methodology of feature set. We use develop 6 to 10 facial landmark extraction for generative features, and then we use consider established comparisons for proper validation. So this picture depicts how develop 6 to 10 model gives us a 6 to 8 landmarks. We use distance features as a ratio and angle features. So we chose the ANT's model for face recognition as an established feature. We chose 9 instances, and each of the distance is used as a ratio. For ANT's model, let's use how it works. For this 9 pictures of 3% each, it can be observed that the features are pretty much same for a particular person, but they are varying for a different person. But this is only in case of when there is the absence of smile. So ANK's model were trained on neural faces, and they are not trained on smiley faces, so we don't expect them to work fine on smiley faces. So for example, like in this picture, we can see that for two different persons' smile face, the features can be similar. So, so for ANK's model, it is not pretty much evident that they will be uh, detected differently. So again, in this case, we can see that for a particular person in different smiles, the features are pretty much different. Uh, so this model can make detect these two pictures of different person, but same person. So yeah, there these are the limitations of technology features. So for our newer approach, we observe the smiley faces of different persons and try to gain some insights of how new smile-based features should be. We also include the neutral faces features to just ensure that there is enhancement of uh, facial detection and recognition. So for this purpose, we use UVNMO Smile dataset, and this is a good dataset with 400 subjects, and uh, each of for each of the subjects there are at least 4 videos, and for a particular video, almost for every video, after 1/4 of the frames, the smile starts and ends before three, 3/4 of the frames. So we consider these internal middle frames and extract 5 to 10 frames from each video at random, and we consider these frames for this uh, we consider these frames for the uh, body training. So for our flow diagram, it will be like we consider the dataset and extract the images from each video, and then we extract landmarks from each of these pictures, and we calculate and save the features and ratios. Then we train a model on this extracted data and extracted features, and then we just use this model to run the tests. So for our new distance features, there are 12 new distance features. So these pictures demonstrate how these features are actually. So it can be observed that these features are pretty much similar for a person in different smiles, and they're pretty much different for smiles of different persons. So these features can be used as uh, for detection. So these are the modes for distance features, and these are most of them. And for angular features, we have 16 more angular features, and these features demonstrate how these angular features will remain similar and can be used to detect. So, so these pictures demonstrate them, and so our expectation from this model is we use this mile-based unique features, and we also included the neutral-based unique features. So we expect our model to combine them and work well on, on the whole data set. So let's demonstrate how these new features are unique. So for our new features uniqueness, we can see that our new features that our new features may remain similar on the interfaces of two different persons, but they are pretty much evidently different on two different persons' smile. So again, another two features we can demonstrate here. They are pretty much similar on different persons' neutral face, but they are evidently different on different persons' smile. So again, there are some more features. So there are some potential lackings that we didn't actually have that much big enough database. So we used UVNMO, and we actually extracted a lot of features from a particular video. So there was less variation on these pictures, and of course we use the delete 68 landmark predictor, and it does not work on post variation and uploaded faces. So in presence of this link in these cases, our model may not.
For classification we used different machine learning classifiers, among them SVM, random forests, linear discriminant analysis, linear regression works better. Decision trees, k-nearest neighbor, naive Bayes, gradient boosting machine does not work well. It will be clear after seeing classifiers comparison. Here are some test accuracy using different classifiers recognizing persons by landmark features. We can see SVM, random forest, linear discriminant analysis, linear regressions accuracies are more than 80%. Linear discriminant analysis performs very well. Its accuracy is above 90%. Other performs poorly. So, we used SVM, random forests, linear discriminant analysis, linear algebra for classifying. We used different models using different classifiers and different type of feature sets. Models are consisting of either only angle features or only distance features, or both angle and distance features. Using different types of features result in different accuracy. We can see, only angle features performs poorly for every classifiers. Results are almost similar for other two cases. Support vector machine and linear discriminant analysis performs better using only distance features. But random forest and linear regression performs slightly better using both kinds of features. For some models angle features are redundant, because when we use many distances, almost all angles are included indirectly. But some models work better when we include all features. We extended the A and K's model. Our target was to increase the accuracy taking more facial features, especially smile-related features. Here are some comparison of A and K's features on neutral images and our features on smiling images. As we can see, only naive Bayes model works better for the old model, though its accuracy is very low. Every other classifiers using our features perform way better than the old model. Performance differences are almost 30%. We used old features for neutral images, and some additional new features for smiling images. This comparison is to show only that our new features performs better than old features. This comparison cannot show the impact of smile on faces while recognizing persons. For these we need to apply same features to both neutral images and smiling images. Here is a comparison between neutral and smiling images using only old feature set. Though the accuracy is not good enough, but they are very close. Only random forest model performs better on neutral images. All other model performs better on smiling images. This is the comparison between neutral and smiling model when using additional new features. Here accuracy is good. Here we can clearly see that smiling images can be recognized with better accuracy than neutral images. One more thing to show. We test the model with this variations. First we train the model with neutral images, and test them with neutral and smiling images, then train with smiling images, and test with neutral and smiling images. We can see, cross-testing accuracy is very low. From the results, we can say that linear discriminant analysis works better than any other classifier in landmark-based face recognition. With smile on face, recognition accuracy is slightly higher. Model that is trained with smiling images cannot do well recognizing neutral images and vice versa. Our works can be taken forward in these cases. We can incorporate smile detection model with our model. When smile is detected, smiling model will be used, otherwise neutral model will be used. Features change gradually from start to broadest smile, tends to remain same for a person. This can be used recognizing a person more accurately. But there is a challenge here. In many cases, this change is same for blood-related people. To overcome this, our new features can be incorporated.